Good afternoon. My name is Alex, and today I am presenting my GPU Programming Capstone project. This project is part of the Coursera GPU Programming Specialization, where I explored CUDA, parallel processing, and advanced GPU libraries. Since I recently developed software for self-driving cars, where optimizing performance on target hardware is crucial, I was motivated to learn CUDA and explore its capabilities in high-performance computing. My goal for this project was to implement and optimize an edge detection algorithm using CUDA and cuDNN.
This is an example video processed with my implementation. Left the original data and right with the edge detection filter applied.
The Coursera specialization on GPU programming is a set of 4 courses designed to provide learners with the skills to develop high-performance computing applications using GPUs. Throughout this specialization, we explored concurrent programming, parallel programming with CUDA, scaling CUDA applications for multi-GPU setups, and utilizing advanced CUDA libraries. My project focuses on edge detection, which is an essential technique in image processing. Edge detection helps highlight object boundaries and is widely used in fields like computer vision.
Edge detection can be implemented on the basis of a so-called Sobel operator. The Sobel operator is nothing but the intensity gradient of an image in a horizontal or vertical direction, for example. Using cuDNN convolutions, you can compute these gradients in multiple directions in a single step by defining a convolution kernel that has an output channel for each gradient direction.
I started with NVIDIA's NPP library and later transitioned to cuDNN as a learning exercise.
The main purpose of cuDNN is to implement efficient deep neural networks. One of the basic building blocks for neural networks in image processing is the so-called convolution or cross-correlation. Implementing a convolution based on cuDNN functions is quite verbose. Therefore, I introduced the convolution class that manages descriptors and memory, together with the apply method that takes an input and an output image as arguments and applies the forward pass of a cuDNN convolution. The convolution class provides a clean interface that is reduced to the required functionality.
One challenge was that cuDNN does not directly support certain NPP functions, so I had to develop custom implementations as CUDA kernel functions. My learning objective at this stage was to understand cuDNN rather than focus on finding a runtime optimal solution.
Functionalities like converting an image between 8-bit integer and floating point representation are quickly implemented as an CUDA kernel. The kernel pointwise halo provides some magic to combine the original input image with the edges.
After replacing the NPP parts with cuDNN code, I wanted to improve the runtime. To boost performance, I optimized memory management and leveraged CUDA graphs to streamline execution. CUDA graphs are a more recent development in the CUDA space, as far as I know. This might be the reason why CUDA graphs are not represented in the Coursera calls. The runtime data collected during the project clearly demonstrate improvements in execution time with these optimizations.
Starting from a naive implementation, I could reduce the execution time from 42 milliseconds to roughly 20 milliseconds per video frame, which is an improvement of more than 50%. When subtracting the runtime that is needed for file I/O and for memory transfer between CPU and GPU, the reduction is even more impressive. The runtime on the GPU alone drops from 34 milliseconds to below 6 milliseconds, which is a reduction of around about 80%. Let's have a look at the details. In a first naive implementation of the convolution class, I did all the creation and destruction of those cuDNN descriptors inside the apply method. So that was repeated for each and every frame that needs to be processed for a video clip. In the updated version, I moved these management tasks into the constructor and destructor of the class. This change resulted in the most significant runtime reduction during my optimization efforts. The most important thing that I learned here was what not to do. Don't repeat creation and destruction of descriptors in cuDNN. As already discussed, I also wanted to learn about CUDA graphs. A CUDA graph records calls to CUDA kernels and is able to replay them at a later point in time. This change involved a major refactoring of the project, which is why a discussion in detail would go beyond the scope of this video clip. The interested audience is referred to the pull request that introduces this change. Again, the runtime drops by a few percent. By the way, you may find a list of links below.
My implementation successfully detects edges in images in a visually refined manner. While the primary focus was not on achieving optimal performance, I was able to observe measurable improvements in execution time after applying CUDA graphs and memory optimizations. The collected runtime data highlights the impact of these optimizations on the runtime performance. For future improvements, one should consider optimizing the runtime further, refining the memory management, implementing integer quantization, and enabling batch processing of multiple video frames at once. Additionally, incorporating multi-threading on the CPU should enhance I/O performance when processing a continuous stream of video frames, potentially leading to an even more efficient and responsive implementation. This project was a fantastic learning experience, and I am looking forward to applying CUDA and cuDNN to real-world problems. Thank you for watching.